Hello friends, this is session 15 and this session is going to deal with probabilistic models. So probabilistic AI models. Let's get started. Here is the agenda for today's session. We are going to begin by describing what probabilistic models are and why they are important. Okay, that's going to be the first thing on our agenda. We will then proceed to build probabilistic models, and here we will talk about generative versus discriminative models, terminology that you have seen earlier, and we will see how that links to the probabilities, the way the probabilities are used. The next thing on the agenda today is to study three important classical probabilistic models: the naive Bayes, the GDA or the Gaussian Discriminant Analysis, and Logistic Regression. So we will study these three models in detail. And finally, we are going to end with a comparison of how these models perform on different types of data. So that's the agenda for today. It's a packed agenda. Let's move on with it. Okay, so what are probabilistic models and why do you need them in the first place? Consider the simple linear classifier that we studied many lectures ago, right? And what we did was we said that if we were given some training data, this was training data, supervised learning, of course. So you knew how the training data was classified. You came up with the best linear separator. And you said that the linear classification of our classification output was going to be the sign of W transpose xk. Xk here is the vector of input dimensions and Wt is your best weights, okay, which you determined by doing probably gradient descent or some such optimization algorithm. Your classification output was sign of W transpose xk. This is what we said was the linear classifier. Now, when we talked about the linear classifier, we already knew that there was going to be an overall probability of error. We knew that our classifier would not give us the correct answer 100% of the time. It would give us wrong answers a certain number of times, and therefore there was an overall probability of error or an accuracy, overall accuracy that you would associate with your linear classifier. What we need to know, however, is we need to know the confidence the classifier has in each result that it returns. Or in other words, you would like your classifier to tell you the probability of a particular answer being correct, right? Why is this important? In many scenarios, we need the ability to manage risk or calibrate our response per input. I'll get into this in detail, but let us see what I mean by confidence in each result. So suppose you said that the overall accuracy of your classifier was 70%, right? So 70% of, let's say, your validation set, it classified correctly, 30% it made mistakes. And if you were given a random input, you would say the probability of your classifier giving the right answer would be 70%. That's on a random input. However, what you would be interested in knowing is that for a specific input, as opposed to a random input, for a specific input, can your classifier also return the confidence it has in the result? Okay, so can the classifier tell you the level of confidence it has in the result that it has returned? Or in other words, the probability of the answer that it has returned being correct. You would like your classifier to not just classify but also associate a level of confidence with each result that it returns. And this is important because in many cases you need the ability to manage risk. So what are such scenarios? I mean, these scenarios are aplenty, but I'll give you two examples. Medical diagnosis, for example, right? I mean, let us say you sort of running a classifier, you built a classifier to return whether a particular patient is healthy or whether he is ill, depending upon his numerous readings, right? Let's say you have built a classifier for that purpose. Now, as a doctor, you would obviously be interested in knowing with what level of confidence the classifier is predicting the answer. So consider an example where, let us say, the classifier said that a particular person was healthy, right? You would also like to know whether the classifier is very sure that the person is healthy, or it is, sort of sure, not really very sure. Because in that case, you would like to perform further tests, and the way you take that case forward would clearly differ. So that's an example where you would like the classifier to also tell you how sure it is that the person is healthy, right? Another example is fraud detection. Fraud detection, let us say you're analyzing a lot of financial data about a lot of individuals. You would like to know what is the probability that somebody has committed a fraud or somebody has not created a fraud. It is not enough to just say that, okay, this guy has not created a fraud. Because typically what you would do in this case is you would lean in the other direction. Even if there was a small chance that the person has created a fraud, or if you are not very sure that he is clean, you would like to gather more information from that person. Of course, in certain situations, especially in India, this is taken to absurd lengths. I mean, even if there is a very small chance that you've done something wrong, you get flooded with notices asking you for more data, etc., etc. I mean, if the probability is 0.00001 that there is some issue with your financial records, I mean, just by existing, you may actually end up with that probability, and you could, be subjected to notices and so on and so forth. But that's an extreme example. In most sane situations, you would like to know for sure whether a person is clean or whether there is some likelihood that he is creating a fraud. And therefore, in addition to just knowing the classification result, you would also like to know how sure your classifier is of the answer that it is returning. So these are two examples just to indicate that knowing the confidence in each result on a case-by-case basis, knowing the confidence in each result returned by the classifier is important to us. What we need to do therefore is to build models that tell us the probability of the answer being correct for each particular input. Of course, in addition to telling you the answer. Models that tell you the probability of the answer being correct for each particular input. That is what you're looking for. And that is what probabilistic models do. Okay, now because I am going to contrast probabilistic models with our old linear classifier that we studied many lectures ago, let's just do a quick recap. Remember, we were trying to come up with the ideal linear separator, and we defined the loss function, which was a hinge function that looked like this. And we defined the loss as 1 minus yk times zk. Here yk was w transpose xk, so it was the computed output. And zk was the observed output. This yk is the computed output, yeah, and zk is the observed output. So this could be 0 or 1 depending upon what the training sample was classified as. So this is the observed output, this is the computed output. You defined your hinge loss in this manner. You solved this problem using the gradient descent. This was your gradient. And finally, you ended up with a situation where you said that your final classification output on test samples was going to be sine of w transpose xk, where w transpose was the weight vector of your optimum weights that you determined on the basis of training data, right? So this is what your linear classification did, which we studied several lectures ago. Your loss was the hinge function. And as you went further and further away from your linear separator, clearly your loss increased linearly. Loss was 1 minus yk star zk, right? So in many ways, you could think of this as a geometry-based approach. Because you were looking at the distance from the linear separator, and your loss was directly related to the distance or how further you were away from your linear separator. That is why it would be fair to call this a geometry based approach. Your distances that you were dealing with were geometric distances. Okay, so how do probabilistic models differ from these traditional linear classification models that we studied earlier? Okay, our linear classification output was sign of W transpose XK, as we said. And when you see something like this, I mean, the first question that probably came to your minds, even before you went to specific probabilistic models, was can the distance from the boundary, which is this quantity, serve as a measure of confidence? Remember, our classification was sign of W transpose XK. So W transpose XK became larger and larger in the positive direction on one side of this linear separator. It became more and more negative on the other side. I mean, it could be the other way around, but essentially this is what it was. And therefore, it seems reasonable that further the point is from your linear separator, more confident you are about your classification result. Right? So for example, you would say that you were pretty sure that this was going to be mapped blue and this was going to be yellow, as opposed to perhaps points that lie near the linear separator. So can the distance from the boundary, can the geometric distance from the boundary, which is essentially just, this is an indicator of the distance from the boundary, serve as a measure of confidence? Now, just to be very sure, this is a indicator of the distance from the boundary. Okay, I mean, purely from a coordinate geometric perspective, this is not the distance, but this is an indicator of the distance. And can it serve as a measure of your confidence? The answer plausibly seems yes. So then why not just go with that? Why not associate map probabilities to the distance from the linear separator and be done? Why do you require separate probabilistic models? Okay. The first question that you run into if you were to do something like that is, how would you exactly relate the geometric distance to probability? How do you relate geometric distance to probability? Probability goes from 0 to 1. Geometric distance can go from minus infinity to plus infinity. So how do you exactly map one to the other? The second problem that arises is the scaling of parameters. The scaling of parameters should not impact the confidence level, of course. However, let us say that you were to measure a particular reading in grams instead of kilograms. All your distances would become 1,000 times larger, and that would impact the confidence level if it was directly related to the distance. And that is something that you don't want. Purely by changing the unit of measurement, the confidence in your answer should not change. So scaling of parameters should not impact the confidence level, whereas the distance from the boundary does get impacted when you scale the parameters. Account for data distribution in higher dimension. Now this is a slightly tricky point. When you go on to higher dimensions, we have alluded to this before, when you go to higher and higher dimensions, the distances sort of increase, right? Now imagine a scenario where in certain dimensions your distance from the separator was not high, and let us say in just 1 or 2 dimensions it was very high. Now what that would do is that the overall distance would increase, and that would distort the level of confidence if you were mapping the distance to the level of confidence, right? So you want to make sure that the way the data is distributed in higher dimensions should not unduly impact the level of confidence, which it would if you directly map the distance to the confidence level. And finally, performance. I mean, this is an empirical observation. It turns out that the probabilistic models that we are going to talk about in this lecture generally perform much better in terms of estimating probabilities, as opposed to a model where you simply map the distance to a probability or a measure of confidence. So these are the reasons that push us, that encourage us to think of different models based in terms of probabilities, rather than using traditional models and mapping geometric distance to probabilities. right? So hence the need for models that directly optimize in terms of probabilities. Let's cover a few probability basics. These are some things that you've studied in high school, but I want to quickly spend a minute going over them. So let's consider A and B to be two events indicated by the blue and red figure here respectively. Here are some identities that you already know. Probability of A union B, probability of A union B is the probability of A plus probability of B minus probability of A intersection B. So probability of A in this figure is essentially the area in this blue figure, the probability of divided by the total area of the rectangle. Similarly, probability of event B is the area in this red figure divided by the total area. This is the intersection, and union is essentially the entire area covered by either one of the two events A and B. So you know that probability of A union B is A plus B minus A intersection B. This thing comes about because if you just added PA and PB, this area would get counted twice. Similarly, A intersection B, which is this quantity, is probability of A given B multiplied by the probability of B. Now, this is called a conditional probability. Probability of A given B is the probability that the event A occurs given that the event B has already occurred. So in terms of ratios, it would be the ratio of the area of this intersection divided by the area inside the red figure. So that would be probability of A given B, and probability of A intersection B is A given B multiplied by the probability of B. Similarly, probability of, you could interchange B and A. Probability of A intersection B is also probability of B given A multiplied by the probability of A. And therefore, if you sort of equated the right hand sides of these two equations, you get this equation. Or if you just wanted to look at probability of A given B, you get the equation that probability of A given B is probability of B given A multiplied by the ratio of probability A divided by probability of B. So this is an identity that you are hopefully familiar with. I have just derived it here based on equating the right hand sides of these two equations for intersection of A and B. This is the Bayes theorem. Okay, this is the Bayes theorem. You, like I said, I imagine that you know about this already. And it gives the relationship between conditional probabilities. So it gives the relationship between P of A given B and P of B given A. It's simply this multiplied by this particular ratio. Okay. So this is the Bayes theorem. I just wanted to recap that over here. The Bayes theorem is going to come in very handy as we move along and talk about some of the probabilistic models. Okay, now let us come to the schematic that we have been talking along about for several lectures and bring in Bayes theorem into this schematic. So we've said that when you're talking about AI, when you're talking about, you're talking about models, what is it that you are trying to do? We said that there is a target function. There is a target function f that maps the input space x to the output space y. That means there is a target function f that returns an output y I for every input xi. Now x is drawn in capital because x could be a vector. It could be a multi-dimensional vector representing multiple readings that you take and you supply as an input to your target function. So the target function, to recap, maps every input xi to an output yi. And the entire question that we have been dealing with is to find this target function f based on the training data at our disposal. That has been the exercise all along. What are you going to be doing in classification? This is very important. This is important to understand. In the classification, what we would do if we were dealing with probabilities, what we would do is for a given xi, we would find the probability of yi given xi for all yi and then select the yi for which probability of yi given xi is the maximum. Okay, I'm going to explain this in detail. It's very important to understand this because this is the crux of how what all probabilistic models are seeking to achieve. So for example, let us say if you were doing classification, you had two outputs. Y0 is one class, is class 0, let's call it, and Y1 represents class 1, let's say, right? So this is Y0 and Y1, two classes. You could have YA, YB, YC in multi, if it's not binary classification, you could have multiple output classes as well. And you are trying to map each input to one of these classes, right? Now, if you were doing this classification with output classes A, B and C, what would you do? What would you do? For a given xi, let us say you are given a particular input xi, you would find these conditional probabilities. You would find the probability of ya given xi, yb given xi and yc given xi, right? You would find all of these probabilities. You would want to find all of these probabilities. And then you would take the highest of these and you would say, you would assign xi to that particular class, right? So if probability of ya given xi was 0.4, if this was 0.3, 0.3, you would say that xi belongs to class ya. That's what you would do in classification. So you would find the conditional probabilities of the output classes given that input and take the highest probability amongst them and you would return that as the classification result, right? This is what you would try to do. That is exactly what I have said here. The way the classification would work in terms of conditional probabilities is that for a given xi, we would find the conditional output probabilities for all classes given that input because you are given that input, right? I mean, quite obviously. And you are trying to determine what is the conditional probability of each output class given that input for that input and then select the one that has the maximum probability. That is what you would do in classification. So this is absolutely important to understand. Whenever you are dealing with probabilistic models, your aim, your goal, your target is to always determine probability of yi given xi over all output classes, over all yi's, right? For that particular xi. That is your target and then you select the maximum. Now that you are seeing conditional probabilities over here, it's clear that I am going to bring in the Bayes theorem. Let's bring in the Bayes theorem. I have dropped the subscripts I, which denoted specific inputs or specific outputs. I am writing the Bayes theorem in terms of x and y's. Probability of y given x, which is what you always want to find, is equal to probability of x given y multiplied by probability of y divided by probability of x, right? This is just Bayes theorem written in terms of x and y's, events x and y's, instead of a and b that you saw in the earlier figure. And I have on the left hand side, I have kept probability of y given x because as we saw, this is finally the quantity that you are interested in and you are going to determine which y has probability of y given x to be maximum, right? Okay, so this is Bayes theorem written in terms of x and y. Some nomenclature, some terminology I want to introduce over here. Probability of x given y is often referred to as likelihood. Okay, called likelihood because it indicates the likelihood of this particular xi being mapped to a particular class y. Probability p of y is also known as prior. This information is called prior because you typically know the likelihood of classes vis-a-vis each other. Probability of X is also called the evidence or the marginal likelihood. Evidence or the marginal likelihood. And probability finally of Y given X is also known as the posterior probability. The posterior probability, which is what you are interested in. So this is again, like I said, just a little bit of terminology. If you are reading any technical work and if you run into these words, you should know what they stand for. The likelihood, the prior, the evidence, and the posterior probability. Okay. Now that we have established what we would be looking for, which conditional probability is important to us in terms of our problem, let us proceed to solve, or let us proceed to see how these probabilities can be determined. Okay. Now there are numerous probabilistic models, and there are three classical, which are called classical probabilistic models. These are like the basic models that everybody studies, and these are the ones that we are going to cover in this particular lecture. And how do these models differ? These probabilistic models essentially differ from each other on the basis of how data is used to estimate probabilities. Okay, that's the only difference between how these models operate. How is data used to estimate different probabilities? The first model that we are going to study is called the naive Bayes. The naive Bayes model. It's a generative model. Remember the term generative model that we studied in the earlier lecture? It's a generative model, and the reason why it's called a generative model, it models how data is produced. In probabilistic terms, it determines the probability of X given Y and the probability of Y. So when I say it models how data is produced, when something models P of X given Y, what you're effectively saying is, if the correct answer is Y0, what are the inputs that can potentially result in that particular output? So probability of X given Y and probability of Y, which is the independent probability of a particular output. So this is a generative model, and what it does is that like I said, it finds out the RHS. So this is on the RHS. You are, no matter what, you are always interested in probabilities of Y given X. Therefore, naive Bayes algorithm is something that is going to use the Bayes rule. It's going to use the Bayes theorem to compute this quantity and thereby estimate probability of Y given X. Okay. The reason why there is a Bayes in the name is because the Bayes theorem is being used. The reason why it's a generative model, because it begins by estimating probability of X given Y and probability of Y, which are on the right hand side of Bayes rule, and it connects them using Bayes theorem to probability of Y given X. Now, to spend a minute on this, again, why is it called, just because it determines X given Y and probability of Y, why is it called a generative model? Why do we say that it models how data is produced? Why do we say that? Think about it. What it is doing is that, essentially, let us say these are two classes of healthy individuals and persons who are ill. This model tries to determine the distribution of the blue points. In other words, it tries to model what kind of readings are likely to be produced by healthy individuals, what kind of readings are likely to be produced by people who are ill. So it models how this data was likely to be created. In other words, it models the distribution of X given Y. It finds the probability of X given Y, and therefore we call it a generative model. Okay, great. So this is the first model that we are going to study, the naive Bayes. What I have not described yet is why the word naive, and that we will explain when we look at this model in detail. The next model that we are going to talk about is the GDA, the Gaussian Discriminant Analysis. it is also a generative model. It is also a generative model. It models how data is produced, and in other words, it models probability of X given Y and probability of Y. Okay. Now, how does it differ from naive Bayes? How does it differ from naive Bayes? It only differs in the assumptions that you make on data. So the assumptions that are made on the data in naive Bayes are different from the assumptions you make on the data on the Gaussian discriminative analysis, and therefore depending upon which assumptions hold in your particular case for your particular problem, you would decide what approach to go with. Both are generative models. The final model that we are going to study today is the logistic regression model. This is a discriminative model. This is a discriminative model. In other words, it directly models probability of Y given X. This is what you are always interested in, like I said, and it directly models Y given X. So what it does is it directly finds the separator. It directly finds the separator. It directly tells you what is the probability of the answer being Y0 and the answer being Y1 for each particular Xi. And therefore you can imagine that it is effectively creating a separator. If it's directly going to estimate the probability of this class versus that class, in other words, it is essentially drawing the decision boundary for you. So that is logistic regression, and that is the third model that we are going to study today. Now, when you look at these three things and when you look at the Bayes theorem, the question that perhaps still continues to trouble you is, why are there these different approaches? And if there is the Bayes theorem anyway, if all of these are related with this equation right here, why does it matter which one you compute? I mean, you could begin by just computing this instead of computing this and this first and then finding it out. I mean, what's the big deal? That's the question that should be bothering you at this time. Why are there different approaches? And I'm going to spend some time explaining why there are these different models. And although all of these probabilities are related with Bayes' rule, why does one model work better than the other in certain scenarios? That's what I'm going to explain to you in the next slide. Okay, now if I am going to bring some clarity to the table, first there needs to be some confusion in your minds, right? So let's begin by creating that confusion before we bring clarity. So imagine a situation where you are trying to estimate the loan risk. Okay, you are trying to estimate the loan risk for different demographics. So you collected data on the basis of age and gender, and you have essentially classified age as young and old and gender male and female, right? And you created 4 groups: high risk, low risk, very high risk, very low risk, let us say. And then you've done this mapping, you've collected this data, and you have classified this training data into various groups depending upon what happened, how they misused the loan that was given to them, so on and so forth. So for example, you had a young female who who did not return the money, and therefore she was assigned to group C. There was a old male who was assigned to group A, and so on and so forth. This is your training data. This is your training data, right? This is your training data. Now you can estimate the probability of various events directly from this table, right? So if you wanted to estimate the probability of a young female being in the high risk zone, for example, what would you do? You would look at all rows that involved young female, and then you would see what percentage of those belong to class C. Or for example, if you were trying to do the same exercise for young males, you would highlight all the rows that involved a young male. You would highlight all the rows that involved a young male, and the probability of young male belonging to group B would be the number of young males lying in group B divided by the total rows involving young males, so on and so forth, right? So you could get those probabilities from this table. You could also get the converse probabilities from this table. If you wanted the probability of someone being a young male when he was a low risk in terms of loans, you would find all the rows that belong to group B over here, and then find what percentage of those were young males. So if you are given a table like this, you could pretty much find the conditional probabilities in both directions by simple counting, right? So this would lead you to the question, the same question that I asked earlier. If the conditional probabilities both ways are related, in fact, in this particular table, in this particular data, you don't even need to go to Bayes theorem. You can actually count. You can count in the correct manner, and you can determine both the conditional probabilities, A given B and B given A, just simply by counting, right? Like I just demonstrated. The question that would bother you at this time is whether Bayes theorem is needed at all. I mean, earlier I said because there is Bayes theorem, what is the big deal? You could go either way. Now I am saying that if you are given a data like this, I am making an even more confusing statement. If you are given data like this, you could directly determine the probabilities both ways, even without recourse to Bayes theorem, right? So if that is true, if this is the kind of data you are gathering, what is the conceptual difference between generative and discriminating? What is the conceptual difference? Surely the difference is not a computational difference, right? I mean, what's the big deal if you are, sort of computing the RHS first or computing the LHS first? That cannot be such a big deal. So clearly there is a conceptual difference between generative and discriminative. And what is that conceptual difference? Right? So this is the question that should bother you. I hope I have created a little bit of confusion in your minds, or at least raise a question in your minds as to, why are we doing all this? I mean, if this is the nature of data, if you have Bayes theorem, why are we talking about generative, discriminative, as if these were two vastly different things, right? Okay. So having created that confusion, it is now time to clear that confusion, get some answers. Okay. The first thing to bear in mind is that the Bayes theorem also applies for continuous variables. That means it applies to probability density functions as well. Everybody knows what probability density functions are, I assume, and therefore I have written Bayes theorem in terms of probability density functions. F, G, here I'm not using the alphabet P, which we were using for discrete variables. I am using these small case alphabets to indicate that these are functions. These are probability density functions, and the Bayes theorem applies to probability density functions as well. Very, very, very important to understand. Why is that important to understand? A couple of things about probability density function. The probability density function at any particular, the probability at any particular value for continuous variable is going to be 0, right? So the probability, if you cannot say, if this was your probability density function, you cannot say that the probability of this, sorry, my drawing is not that great. I'll redraw it over here. If this was your probability density function, you are not going to say that the probability of this particular event happening, the probability of this particular value happening is equal to this. That is not the way probability density function works. The probability of a specific value being assumed when you are talking about continuous variables is 0, right? What the probability density function indicates is the relative probabilities. It integrates the relative probabilities, and if you wanted to find the probability of a particular value being taken, you would need to take a small interval around that value, evaluate the integral around that value, and that would give you the probability. That is what a probability density function is. And then if you make the interval smaller and smaller and smaller, obviously it would become, the value of that thing would become 0, right? So that is what the probability density function is. But the Bayes theorem applies to applies for continuous variables. It applies to probability density functions. Okay, and remember, PDFs indicate relative probability, whereas the integrals around any value would give you the probability. Okay, so coming back to our point, Bayes' theorem applies to continuous variables as well, and that's what makes all the difference. Now, why does it make all the difference? It makes all the difference because your data is going to be finite. Your training data is going to be finite. And therefore you are going to evaluate the training data for discrete values of inputs. Now, for example, age per se is a continuous variable, but you would probably have somebody 43 years old, 27 years old, so on and so forth, right? And you are going to have certain finite number of discrete values for age. Now, I have chosen young and old over here. I have sort of I have not used continuous variables in this figure, which is what leads to the confusion whether Bayes' theorem is required at all. But when you are dealing with continuous variables and you realize that your training data is finite, things change. So age, which is a continuous variable, you are only going to capture the age for specific values of age. Gender, well, I mean, bad example to take. Gender is not a continuous variable. At least in the traditional sense, it's not a continuous variable. And but if you were to talk about continuous variables, so again you would have certain specific values of that continuous variable in your data. That makes a difference. That makes a big difference. And the conceptual difference between generative and discriminative lies in the fact that your choice of method is going to be influenced by the amount of data and other a priori knowledge. Example, the distributions of the density functions. Okay, so if you knew what a particular density function looked like, you could use that a priori information. To get better results. And of course, the amount of data. If you are going to model probability density functions on the basis of finite data, clearly you can imagine that you could do it better one way as opposed to another, right? So the entire difference between generative and discriminative and why some work better in certain cases vis-a-vis others has to do with the amount of data at your disposal, the fact that you are almost always dealing with continuous variables on the input side, and you often have a priori knowledge of the distributions of certain input variables. That is what makes all the difference between generative and discriminative. Actually, wait a minute. This notation that I have used here is unfortunate. I should not say that f of a equals to 0. I should not say f of a equal to 0. F is obviously a function. I should say probability of a is 0 for a specific a. Okay. So if you're talking about continuous variables, the probability that a specific value of a occurs is 0. Right? It's vanishingly small. And if you want to, what you can do is you can find out the value of the function in a small, the probability of the variable taking a value in an interval, and that would be the integral over the probability density function. So sorry about this notation. I think this is unfortunate. I should probably say probability of a is 0 for any a. Okay, having said that, let us move on now to discuss the three classical probabilistic models that we spoke about. And the first model that we are going to consider is the naive Bayes. So this is the Bayes theorem in terms of probability density functions. And as usual, I have taken a capital X to denote the fact that X is a vector. It could comprise of a number of input variables, independent variables. Okay, now given this fact, for a particular value of x, e of x is going to be constant, and therefore you can say that f of y given x, which is the quantity you are interested in, is proportional to g of x given y multiplied by h of y. Right? So because e of x is constant across all y's given a particular x. What is the naive assumption that is made in the naive Bayes classifier? What is the naive assumption? The naive assumption is that the variables, which means the components of x, are independent. So the assumption that is made is that x1, x2, x3, etc. are independent, in the sense the value that x2 takes does not depend upon what value x1 has taken. These are independent variables. That is the naive assumption. What is the meaning of the word naive? Naive means innocent or ignorant. And what we are essentially saying is that we don't know how the independent components of x are related, and therefore we make the assumption that they are independent. So we innocently make the assumption that these are independent. x1, x2, x3, x4, etc. are independent. The components of x are independent, and therefore probability of A intersection B becomes probability of B multiplied by the probability of A, or in other words, probability of Gx x vector given y, probability of g x vector given y is equal to probability of g1 x1 given y multiplied by the probability x2 given y, x3 given y, and so on and so forth. So this has replaced probability of g capital X, which is the vector given y, right? So what we are saying is that the probability of getting a vector x with specific individual values is the same as the multiplication of those individual values appearing. That's what we are saying. That is the independent assumption that we have made. We have made this independent assumption because we do not know any better, and that is why the word naive comes about. Naive Bayes. Okay. What we are therefore going to do in the naive Bayes is that we are going to evaluate this RHS. We are going to evaluate this RHS for each y. So if this were a binary classifier, there would be two output values of y, y0 and y1, and you would evaluate this quantity, you would evaluate this RHS for y0, for y equal to y0, and for y equal to y1, and then you would compare which of the two is higher to get the higher f of y given x. So if f of y0 given x was greater than f of y1 given x, you would decide that this input should classify to the set y0. That is what you are going to do. So you are going to determine the RHS for each y to get the relative values of f of y given x and choose the highest. This is what we are going to do. Fairly straightforward. Now, the naive assumption, though it is born out of our essential lack of knowledge, lack of insight into how these components of x are related, therefore we say that we'll make the assumption that they are independent, right? This naive assumption actually significantly reduces the complexity of the model and hence the training data required. So the naive assumption actually does two things. Firstly, it allows us to evaluate this. In a simplified sort of a fashion. It significantly reduces the model complexity because it completely disregards any correlation between the components of x, and therefore the training data required is small. Why is the training data required small? Remember, if we go back to our theory of learning, we have always said that lesser the complexity of the model, lesser the training data that is required, right? So the variance error will start going down if you use a model of lower complexity, which is what the naive Bayes actually is. So the naive assumption implies that the naive Bayes algorithm has reduced complexity, and therefore its performance on lesser amount of training data is better. Okay. Let's take an example. Let's take an example to explain what we have done here. Email spam detection. This is a common example or a common application of naive Bayes. And what we are going to do here is classify each email as a spam or not spam. Depending upon occurrences of specific words. what we are going to do is use what is known as a Bernoulli naive Bayes. That means you're going to create an input vector x, and the value, the individual components of that vector x are going to take values 1 or 0 only, depending upon whether the specific word occurs or not occurs. So if it does not occur, you assign a value 0. If it occurs, you put a value 1. Okay, so this is the vector x. The vector x is the vector of specific word occurrences. Now, as we said in the earlier slide, we said that f of y given x is proportional to this quantity as per naive Bayes. And the question is, how do you go about evaluating each of these quantities, right? How do you go about determining each of these quantities? Well, that is fairly simple. You assume that you have been given training data. It's supervised learning. So you assume that you have been given some training data which is classified as spam or not spam, and what you are simply going to do is determine these probabilities for each of the two classes, spam and not spam. In other words, what you are going to do, well, like I said, the training data is a set of emails classified as spammed or not spam. How are you going to determine G1, G2, G3, etc.? Well, by simply counting, right? So how you are going to do it is G1 of x1 given y0, right? So you want G1 of x1 given y0 and x1 given y1, so on and so forth. You have to compute that. G1 of x1 given y0 is the probability that the word x1 occurs in y0. So in the category y0. So what you do is, for a particular word x1 and class y0, this is the ratio of the number of emails in class y0 in which the word x1 appears, divided by the total number of emails in that class y0, right? So I'll repeat. You have to find G1 of x1 given y, y1 and y0, G2 of x2 given y0 and y1, and so on and so forth. How would you go about finding all of those? For example, G1 of x1 given y0, that means the probability that the word x1 appears in emails that are classified as not spam, is simply the ratio of the number of emails in class y0 in which the word x1 appeared, divided by the total number of emails, of course. I mean, it's the ratio, like I said, right? So this is how you go about finding G1 x1 given y0, x2 given y0, x3 given y0. Similarly, you will find G1 x1 given y1 multiplied by G2 x2 given y1, and so on and so forth. And then you would evaluate these. To get the relative values of f of y0 given x and f of y1 given x, and you would classify the email as spam or not spam depending upon which of them was greater. Now there is another quantity here, h of y, which is the probability of an email being a spam versus not spam, and from the training set you can simply define that as the ratio of the spam and not spam emails, the number of spams divided by the total the emails given to you in the training data, and so on, right? So this is how you actually evaluate this RHS and get the LHS, and therefore find the highest f of y given x. So this is a simple example of a naive Bayes classifier used for email spam detection. Now, what happens when you have zero occurrences? Now, it's of course possible that depending upon your training data, you may not have, just adequate emails, and some of these probabilities may actually be zero. Because let's say the word x1 did not appear in any email which was in the class y0, and in that case you would get G1 of x1 given y0 equal to 0, and everything would evaluate to 0, and that's not good. So typically the way these probabilities are calculated is not just to take the direct ratios, but actually add 1 to the denominator and add 2 to the add 1 to the numerator, add 2 to the denominator. 1 you add because you add 1 to the count, and you add 2 to the denominator because that is equal to the number of classes that you have. And this ensures that the ratio, the probability is not 0. It ensures that it stays below 1, and you get better answers this way. So this is what you do. This is just a hack to ensure that you do not end up with 0 probabilities and thereby mess up your right hand side. Okay, so this is what I have said. Determine the RHS for each y to get the relative values of f of y given x and choose the highest. Another application of naive Bayes could be diabetes detection, where you classify each patient as diabetic or non-diabetic depending upon their test readings. Let's say Y0 is the class of people who are not diabetic, Y1 is diabetic, and let us say your X is the vector of readings: blood pressure, body mass index, glucose level, and so on and so forth. And again, you would do exactly the same thing. You would begin by saying that f of y given x is going to be proportional to these things, and you would determine each of these probabilities. How would you determine them? First, you would look at class y0. In class y0, you would find the probability density function of x1 given y. So how the blood pressure varies amongst non-diabetic patients, that would give you g1 of x1 given y. You would do the same thing for BMI and so on and so forth, and you would basically then plug in, when given a new input, you would plug in the values to get y of f of y given x. Now BP, BMI, glucose level, etc., are continuous variables. So what do we do here? We are going to essentially make the assumption that the RHS distributions are Gaussian. Okay, so you are going to assume that these probability density functions, they are Gaussian in nature, and once you assume that they are Gaussian, all you need to do is you need to estimate the mu, which is the mean, and the variance from the available training data. Now these are easy to estimate, right? So you assume that a certain distribution is Gaussian. You have certain numbers, amount of training data, finite training data that you have been given, and since you assume that it's Gaussian, my Gaussian doesn't look all that great, but it is a Gaussian. All you need to do to define this density function is to find its mu and sigma, which can be found from the training data available to you, and then your distribution, your Gaussian distribution function, is basically just this, right? So for a test patient, when you are given a vector of readings, you can find out, given the x, you can find out what g1 of x given y is for that particular reading, because now you have the continuous curve. I keep saying distribution. I should always be saying density functions, probability density functions. Okay. Now, evaluating the LHS in this situation directly may not be possible, or it would lead to horrendous answers, and therefore naive Bayes is useful. So I was making the point all along in the beginning, why do you need something like naive Bayes? Why do you need the Bayes theorem? It is because of situations like these, where you can make the Gaussian assumption. You can make the Gaussian assumption on your RHS variables, and that allows you to simply compute mu and sigma from your finite number of training examples, allows you to compute this curve, and then merrily go about using this curve for any test data that you run into. Okay, so this is how naive Bayes comes in handy. Now let us talk about the Gaussian Discriminant Analysis, which is the second probabilistic model, the second classical probabilistic model that we are going to talk about today. So what is the Gaussian Discriminant Analysis? It is very similar to naive Bayes, except that it does not make the independent assumption. Okay. It also determines P of x given y and P of y. In that sense, it is a generative algorithm, but it does not make the naive assumption that is made by the naive Bayes. So what does it do? It makes a different assumption. Okay. The difference with naive Bayes, like I said, it lies in how X is modeled. How X is modeled. GDA does not assume that the input variables are independent. They can be correlated. They can be correlated. And the assumption that the GDA makes is that they are correlated, but it assumes a multivariate Gaussian distribution over those variables. So it assumes that they are correlated, but that the distribution of those variables is multivariate Gaussian. That's the assumption that the Gaussian discriminant analysis makes. So let's see how this works out. So what is a multivariate Gaussian distribution? I mean, I have just taken an example of a 2D case, a two-dimensional case. This is what it would look like. This is what it would look like. And in this plane, it would look like an ellipse, right? So think of it as sort of this Gaussian curve, but this cap is not symmetric from all directions. Okay, so that is what this is. This is what a multivariate Gaussian distribution looks like. In 2 dimensions and in more dimensions, you can define the probability density function of a multivariate Gaussian distribution. In 2 dimensions, this is the equation. The means for the 2 variables, I have used the 2 variables x and y over here, are mu x and mu y. Standard deviations are sigma x and sigma y, and the correlation between the 2 variables is rho. And given those variables, this is the equation of a probability density function that is a multivariate Gaussian. Okay, so similarly you will have equations in more and more dimensions. How do you calculate the mu's and the sigmas? Well, you calculate them using the standard equations. So the mu's are essentially the mean. The sigmas are the standard deviations, which are calculated in this way, where n is the number of points you have over which you are doing the calculation. Here mu is the mean that you have already calculated. And the rho, which is the correlation between x and y, is the covariance xy divided by sigma x sigma y, which is essentially given by this equation. This should have been an n. Okay, so this is the way you calculate mu, sigma and rho, and you can plug them into this equation to give you the probability density function in 2 dimensions. And you do a similar thing. The equations become more and more complex, of course, but they exist, and that is how you can compute the multivariate Gaussian. Okay. So let us look at an application, right? So throwing those equations, you kind of broadly understand what I was saying, but let us look at a specific application to understand how exactly you would do those computations. So let us say you are trying to build a default predictor. You want to classify loan applications as high risk or low risk by computing a probability of default. So I'm going to take a vector x, which is my vector of inputs, as comprising of the income and debt of that particular person. My default predictor is going to rely on 2 inputs: person's income and the person's debt that he has at any point in time. Okay. How will you go about solving this problem? Clearly, there are 2 categories. Y0 is equal to safe. Let's say it's safe to give a loan to that person. And Y1 is the category that the person is a defaulter, right? And you want to find the probability of him being a defaulter. We are building probabilistic models, so it's not enough to just predict whether a person is safe or a defaulter. You also want to find the probability of him being a defaulter, of him being safe, whatever, right? I mean, there's just 2 classes, So the second probability is 1 minus the first probability. Okay, so how will you go about doing it? What is your training data? What is your training data? Your training data is a set of these values, these vectors for people who defaulted and who were safe. Who did not default, meaning who were safe. So your training data has a number of people in the safe class, it has a number of people in the defaulter class, and for each of those you know the values of these vectors. These vectors are available to you. The first thing you do is you find the priors for each output class. So if you are given, if you had selected your training data randomly, you would have a certain number of safe peoples, you would have a certain number of people who had defaulted, and those ratios would directly be the priors. Okay, so the number of safe people in your training sample would be the prior for the ratio would be the prior probability for the safe class, and conversely for the defaulter class. So you can find the priors pretty easily. The second thing you do is you find the means and variances of the variables for each class, right? Y. That is the mean of the income and debt for safe and default. That's the next thing you do. Then you compute the correlation matrix for each output class Y. Now here the correlation matrix is just, there's just two variables, so there is just one correlation, rho of xy. So it's just one quantity that you have to find, because the correlation matrix is going to look like this. Rho of xy, this is my rho by the way, and this is what your correlation matrix is going to be. But I use the term correlation matrix because if your input had a number of variables in the vector, this would be a bigger matrix, right? So you compute the correlation matrix for each output class Y. Then you model the multivariate Gaussian for each output class Y. So for the safe class and for the defaulter class, you would have a multivariate Gaussian each. There would be a multivariate Gaussian for this, there would be a multivariate Gaussian for this, and those can be modeled after you have found the means and the variance and the correlation for each of those classes respectively, like we saw in the earlier slide, the equations. Finally, when you are given a test point x, what you do is you evaluate g of x given y multiplied by h of y for each class, for each of these two classes, and then take the largest amongst them, because that by Bayes' theorem would give you the largest f of y given x, which is what you were looking for. So that is how you go about using the GDA. That is how you go about using the Gaussian Discriminant Analysis to get the probability of default. Now, why is it not a good idea to use, let's say, a naive Bayes in this case? You could have equally well used a naive Bayes, right? The point is that there are examples like these where the income and debt may actually not be independent. Clearly, I mean, in applications like these, when you're going to predict the probability of default on loans, nobody is going to say that the debt of an individual is independent of his income, right? If my monthly income was 30,000 rupees, my debt is likely to be somewhat, in proportion to that. It might be 2, 3, 4 lakh rupees. It will not be 500 crores, right? Whereas if my income was proportionately higher, my debt would likely to be higher as well. So clearly debt and income are related. Clearly, when you are trying to find out, when you're trying to implement a default predictor, the financial parameters that you take into consideration are all likely to be related to each other, and therefore going with a GDA, which is a multivariate Gaussian, makes more sense rather than making the naive Bayes assumption where you say that all of these are independent of each other. That assumption would obviously not hold, right? So here is an example of where GDA would come in handy. Now let us talk about logistic regression. Logistic regression is the last of the three classical probabilistic models that we are going to cover in our session today, and it's an important one. So let us see what logistic regression is. Logistic regression is a technique to perform classification. Okay, it's a technique to perform classification, usually binary classification. It does not predict values, and the name is misleading. So, in this course so far, we have referred to regression as the technique whereby we build a model to predict values, predict the output on the basis of inputs in output values. Whereas classification is a technique where we classify an input into one of multiple categories. The name logistic regression, although it has the word regression in it, is actually a classification technique. Specifically, most often it is used as a binary classification technique. So remember, the name is misleading. Okay, now I want to go back to what we talked about when we were discussing the linear classification, the binary linear classification, and we said that the output of a binary linear classifier is given as sign of W transpose xk, where xk is the vector of inputs and W is the vector of your optimized weights, right? And depending upon whether the output is plus or minus, you classify that input into one of those two categories. So that is how linear classification works. I have just shown a diagram over here. This is, for example, the training data, and perhaps the best classifier, the best linear classifier was this particular line right here, which essentially is used to determine whether a test input falls on this side or this side, and then it gets classified to the yellow group or the blue group. So this is the binary linear classification that we have talked about. We also said earlier in this lecture, that the distance from the boundary, the distance from the classification boundary, the distance from the separator, which is proportional to this quantity W transpose xk, can it serve as a measure of confidence? We remember in probabilistic models, we are looking for a measure of confidence, or we are looking for a probability or associated with every output, and it was intuitive to assume that the distance from the separator could perhaps act as that measure of confidence. The question we said was, how would you map this quantity W transpose xk, which goes from plus infinity to minus infinity? How would you relate that to a probability which goes from 0 to 1, right? So how do you relate z equal to W transpose x to a probability p which goes from 0 to 1? Recollect, we said that if this W transpose x, if this was the separator, the value of W transpose x would increase, become more and more positive in one direction, become more and more negative in the other direction, and therefore we said that this could be a good indicator of the measure of confidence. So question is, how do you relate this? How do you relate this quantity? How do you relate this quantity to a probability? How do you map this to this? Right? So that's the question. Here is a candidate. Here is a possible candidate to map Z. This I am going to denote by the alphabet Z. Here is a candidate that maps Z to P. Right? So P equal to 1 upon 1 plus e to the power minus Z. Okay, Z, Z, I sort of use them interchangeably. P the probability is equal to 1 upon 1 plus e to the power minus Z. So that is a possible candidate that would map Z, which goes from minus infinity to plus infinity, to P, which goes from 0 to 1. This function is also known as the sigmoid function. It has a name. It's called the sigmoid function. So this is a possible candidate, and let us see what happens if we sort of use this function to map W transpose x to the probability. Now, note one thing, very important to understand this here. Here P is the probability of the point belonging to one of the two classes. Okay, say the yellow class. Let us say z becomes positive in this direction, it becomes more and more negative in this direction. P is the probability of the point belonging to one of two classes, say the yellow class, which I am going to arbitrarily assign the label 1, and the blue class I am going to assign a label 0. Okay, so label 1 is the yellow class where z becomes more and more positive. The blue class has a label 0 where z becomes more and more negative. Now, in the earlier two techniques that we talked about, in the naive Bayes and so on, we associated a probability with every class. Here, because we are talking about binary classification, we can just deal in terms of one quantity, one probability, where let us say if P is greater than 0.5, if P is greater than 0.5, we will predict that the point will belong to class 1, and if P is less than 0.5, we will predict that the class belongs to, let's say, class 0. Say blue. So I'll repeat. P is the probability of the point belonging to one of the two classes, say the yellow class, which has the label 1. If P is greater than 0.5, if P is greater than 0.5, we predict the point will belong to class 1. And if P is less than 0.5, we predict that it belongs to the class 0. So if we can say with higher than 0.5 probability that the point belongs to the class yellow, then of course we call it, we say it belongs to class yellow. And if we can only say that it belongs to class yellow with less than 0.5 probability, chances are that it's a blue point, and therefore we classify it to the class blue. So we are going to use a single probability, and depending upon where it lies, greater than 0.5 or less than 0.5, we will predict that the point belongs to the yellow class or the blue class. Okay, so that is what this P is. That is what this P is. How does this work? When Z becomes more and more positive, this is going to become 0 and P is going to become equal to 1. So as you travel more and more in this direction, P will start approaching 1, right? P will start approaching 1. Now, on the other hand, when Z starts becoming more and more negative, this will start tending towards infinity, which means that P will start going towards 0. Okay, P will start going towards 0 as you go more and more in this direction. So this is P equal to 0.5. Your separator is P equal to 0.5. On this side, you have P going from 0.5 tending closer to 1, and on this side you have P tending to 0, right? So this is how this sigmoid function is going to behave. Okay. Now, what we need to do, I mean, we raised a number of issues earlier in this lecture about, mapping the distance to probabilities and so on. And we said that there were certain challenges, etc. And all we are trying to do now is to address those challenges and come up with a measure of probability that makes sense and that becomes directly the part of our optimization and hence, governs the way our model behaves. So that's what I'm going to go about doing now. P equal to 1 upon 1 plus e to minus z, where z is w transpose x. Remember? Let us introduce some notation here. Let us say y hat of I are the observed labels and they can be 0 or 1 on the training data. So y hat equal to 1 means that it belongs to the yellow class, the point belongs to the yellow class. Y hat equal to 0 means the point belongs to the blue class. 0 and 1 are the labels which are associated with the training data. That is our notation. What we need to do again over here is find the best weights W. Okay, find the best weights W. The optimum decision boundary is found by optimizing an objective function. Remember, we have always been finding the decision boundaries or finding regression planes By optimizing an objective function. There is a function that we need to optimize. It is a function of the weights, and you set up this objective function. You typically either you have a closed form expression, or you set up an iterative mechanism to find the best weights so that the objective function is either maximized or minimized. It could be the mean square error, it could be the hinge loss function, and so on and so forth. The choice of the objective function is in your hands, but it should reflect essentially what you are trying to accomplish, right? So remember, the logistic regression mechanism is still going to give you a separator which is linear, because you are still going to find W transpose, right? You're going to find these weights, and your linear separator is what you are going to eventually get. All we are saying is, instead of using a metric like the hinge loss function or using some sort of a square error, we are going to come up with an objective function that makes sense, because we are dealing with probabilities. So it's clearly going to be linked to probabilities. So the optimum decision boundary is still going to be found by optimizing an objective function. And now I'm going to come up with an objective function in terms of these probabilities that makes sense. Okay. Now, what would we like our weights to do? We would like our W such that P is as close to 1 as possible when Y hat is 1, and 1 minus P is as close to 1 when Y hat is 0. Okay, I'll repeat this. On your training data, you would like P to be as close to 1 as possible when Y hat is 1, because P is an indicator of which class you assign that point to. And if on a training point Y hat was 1, you had already observed on the training point, training data, let's say you were given on the training data that Y hat equal to 1 for a specific point. For that point, you would like P to be as close to 1 as possible, because P equal to 1 is what classifies to that class, right? So this P right here, you would like it to be as close to 1 as possible when Y hat equal to 1, and you would like your W's, remember P is linked to the W's, so you would like to choose the W's such that Z, which is equal to W transpose X, for that particular point, you would like the Z to be such that P is as close to 1 as possible, right? Now what happens for the points where Y hat is 0? What happens at points which have been classified in the training data that are blue in color, for which the label is 0? You would like 1 minus P to be as close to 1. In other words, you would like P to be as close to 0 as possible, right? Remember, when P equal to 0, you are going on the other side, as far away from the separator as possible. And for those blue points, you would therefore like 1 minus P to be as close to 1 as possible when Y hat equal to 0. Okay, so let's set this up then. We define a likelihood function. This is called a likelihood function to maximize. What would you like to maximize? You would like to maximize pi. You know what pi stands for. It's the multiplication of all of these terms. P of I to the power Y hat I multiplied by 1 minus Pi to the power 1 minus Y hat of I. Okay, this is what you would like to maximize. Now let's stare at this equation. Let's stare at this quantity for a minute and see what we are saying. When Y hat of I, this hat has come in the wrong place. When Y hat of I is 1, is 1, 1 minus Y hat of I becomes 0, and therefore this goes away. Okay, and when this is 1, you are effectively maximizing the product of all those PIs. We said that we want the P to be as close to 1 as possible, and when you are maximizing the product of all such PIs, you are effectively saying that you would like all of those PIs to be as close to 1 as possible, right? So this makes sense when Y hat of I equal to 1. What happens when y hat equal to 0? When y hat equal to 0, this becomes 1, this goes away. And for those points, 1 minus y hat of I becomes 1 because y hat is 0. So this is 1. And therefore you are maximizing 1 minus pi for those points. Remember we said 1 minus pi you would like it to be as close to 1 as possible when y hat of I equal to 0. So this product over I of all of these terms, this is a nice compact way of writing it. The product over all training points I, you would like this particular product, to be maximum. You would like to maximize it and you would like to select the W's. So that this product is maximized over all points I. Okay. I'm sorry about this hat disappearing. It's unfortunate, but this is what I'm talking about. Now, if you are going to maximize this thing, because all of these quantities here are positive, you can also maximize its logarithm, right? So the log likelihood function, where you take the log of this quantity, is summation going from I equal to 1 to m. Assume that there are m training points, and you just take the log of what's in here, and the log of what's in here is simply y hat of I log of pi plus 1 minus y hat of I times log of 1 minus pi. And again, this quantity is what you would like to maximize. You've just taken the log over here. Instead of maximizing this quantity, we are simplifying things. We are taking a log and saying that maximizing this is the same thing as maximizing the log of that quantity. Okay. The important thing about logistic regression is the way this log likelihood function has been defined. It's been defined in a rather nifty sort of a manner, and there is a reason why this makes a lot of sense. We will see the benefits of defining it in this manner in the next 2-3 slides. What are we going to do? How are we going to set up our optimization? Again, we want to select the weights. Those are the variables in our control. We want to select the weights so that this quantity I going from 1 to m, where m is the number of points in the training data, you want to maximize. Okay, I have just copied here what we saw in the earlier slide. This log likelihood function is also called the cross entropy function. This is again some terminology that you may run into, and you should know what it stands for. The log likelihood function, which is the log of the likelihood function that we saw, is also called the cross entropy function, which is what we are trying to maximize over W. We will find the best W's, best such that they maximize this function, cross entropy function. Now, you will say that we need to justify why we specifically chose things in this way. Okay, why we chose things in this way. Why did we choose p equal to 1 over 1 plus e to the minus z? Why did we choose a sigmoid function? And why did we choose this sort of a likelihood function or a log likelihood function as the quantity to be maximized? Clearly, there is a choice of many functions that can map minus infinity to infinity to 0 to 1. Why the sigmoid function? And also you could have defined your objective function in many ways. So why choose the log likelihood function? You may ask this question, and that question is entirely justified. We had given such a justification when we used the hinge function in our linear classification optimization. We gave a similar justification when we used the mean square error as the objective function to be minimized when we talked about the linear regression optimization, and therefore I owe you a justification of these choices as well. Now, the first thing I want to say is that this is probabilistically justified, in the sense it is justified in the sense it is it actually does what we want it to do. So sigmoid function is indeed a function that maps minus infinity to infinity to 0 to 1. So it fits the bill. It may be one of the candidates, but it's definitely a candidate. Similarly, the log likelihood function, by maximizing the log likelihood function, you are driving the w's in a direction where the pi's and the yi's get aligned in the manner that we want them to be aligned, right? So there can be no dispute about the fact that these two, the choice of the sigmoid function and the log likelihood function are definitely one candidate. There could be others, right? So these definitely will work. So, but I need to give more justification. So let's move on. This choice of function penalizes confident wrong answers heavily. Confident wrong answers heavily. Okay. Now, what is your nightmare scenario? Your nightmare scenario is where your classifier confidently predicts something that is supposed to be yellow. It predicts it to be blue with a high level of confidence. Okay. That is your nightmare scenario. If it says that its confidence in its answer is low when it does a wrong classification, you could live with that. You could tweak things around. But you want to heavily penalize the wrong answers that are given with high confidence. And I want you to verify that that is indeed the case with the cross entropy function. So suppose you are in a situation where y hat is 0. Okay, if your y hat is for a particular point, let us say y hat is 0 and pi is close to 1, this quantity imposes a heavy penalization in the sense it goes in the opposite direction of where you want it to be. You want to maximize this and you will suffer a penalty in the sense you would be dragged in the negative direction whenever y hat equal to 1 and pi is 0. Okay. Or in other words, when y hat is 0 and when pi is y hat is 0 and pi is 1. So if your y hat and pi are conflicting with each other, that would indicate a confident wrong answer. A confident wrong answer. In those situations, those particular points are going to contribute negatively to the L, dragging it down. Okay, so this is a good thing because it addresses your worst case scenarios very well. You can stare at this for a moment and verify that what I said is indeed true. It's a convex function and therefore useful for the gradient descent approach. Remember, in the gradient descent approach, we want to be assured that the minima that we find is the global minima or the maxima that we find is the global maxima, and that is true for this choice of functions. And finally, the gradient is easy to compute. The gradient is easy to compute. We have always laid great stress on ensuring that the computational burden is minimized, and we will see shortly how that holds in this particular case, how the choice of the sigmoid function and the log likelihood function actually makes things very easy for us, makes it very easy to compute the gradient in the gradient descent. Okay, so that is the justification for using a function like this. Okay, so now let's go about setting up the gradient descent. Let us just consider for simplicity one sample because there will just be a summation over all the training data. There will be a summation over all training data. So for the ease of going through the computation, let's just talk about one single point. So I have dropped the I over here, right? And I have dropped the summation. Now I am maximizing the log likelihood is same as minimizing its negative, right? And that is what I am trying to do. So here P is this and Z is W transpose X, right? And we want to determine the partial derivative of L with respect to W. What do? We are going to use the chain rule. So the partial derivative of L with respect to W is delta L over delta P multiplied by delta P over delta Z multiplied by delta Z over delta W, right? This is your simple chain rule. Now let us find out each of these three. Now delta L over delta P, you can easily verify, is this quantity minus y hat over P plus 1 minus y hat over 1 minus P, and this simply evaluates to this. Okay. What is delta P over delta W? What is delta P over delta W? Delta P over delta Z. That's what I'm going to find. This is the next term to be found, and that's pretty simple too. It is P into 1 minus P. I'll let you do these computations yourselves. And the third term, delta Z over delta W, is simply X, right? All I'm asking you to do is find the derivatives over here and use the chain rule. So if I put all of these three together, let's see what happens. What happens when we put all of these three together and when you substitute into the chain rule? When you substitute into the chain rule, virtually everything cancels out and you are simply left with this, right? This is what I call simplicity. This is simplicity. This is ease of computation that we are talking about. This is the gradient for one sample, and when you are summing over all the training data, you are essentially going to do a summation right here, right? You are essentially going to do a summation right here, and therefore the average over all samples, I'm going to put a 1 over m. Remember, we took averages. I mean, I'm just minimizing the entire sum or minimizing its average against the same thing. That works out to be X transpose, your matrix X of input vectors, times P minus y hat, right? These are vectors as well. This is a matrix. So in vector matrix notation, using the terminology that we have always used in the past, your new W is W old minus alpha, which is your good old step size. You could choose it to be a small positive number, divided by m. M is the total number of training points you had. X transpose is the matrix of input vectors, the P vector minus the y hat vector. P is the vector of all the P's computed on the basis of 1 over 1 plus e to the power minus z, and y hat is of course the vector of observations. So this is your iteration for gradient descent for logistic regression when you choose the sigmoid function and the log likelihood function as the objective function to be maximized or minimized. Put a negative sign and minimize. So this is what it all boils down to. You will agree with me that this is computationally simple. It captures the essence of what we are trying to do, and it maps the probabilities. It maps minus infinity to infinity to probabilities 0 to 1. So what would you do when you are when you are through with computation of the best W's? Let's look at all of that in the next slide. Insights into logistic regression. What we have done is we have created a discriminative model. This is a discriminative model. It's not a generative model because we are directly trying to model probability of y given x, right? We are trying to find a linear separator. That directly tells you whether the input should be classified into this class or this class, depending upon whether P evaluates to greater than 0.5 or less than 0.5. So it's a discriminative model. The class boundary is linear. I have said this a couple of times, but I want to harp on this fact because some people, sort of they get misled into believing that the class boundary is some sort of a sigmoid function. It is not. The sigmoid is what relates W transpose X to the probability. The class boundary continues to be linear because you are finding the best vector of weights W, and your separator is governed by W transpose X. So it is a linear boundary, right? So remember that class boundary is linear, the separator is linear, the probability as a function of the distance, okay, distance is sigmoid. Changing the weight and the bias stretches and moves the sigmoid function to closely fit the training data. So when you're iterating, when you're in the process of finding the best W, what is it exactly that you're trying to do? What you are trying to do, I mean, what happens? So let us say you had certain points that were mapped to +1, right? That were mapped to +1. And that some points that were mapped to zeros, what you are doing by choosing different w's is this constant here. You would wonder what this is. You remember w0, there is a w0 and x0 is actually 1. You remember that? So this is actually w0. But what happens when you are given training data like this is that your sigmoid function is either going to be stretched or moved up and down to basically best fit these given points. Okay, best fit this given points. So that is what it is. I said moves up and down. It doesn't move up and down, it moves left or right. So this is 0 and 1. Obviously the sigmoid function has to output something between 0 and 1. However, the way it moves around is that it can either become a more gentle S, right? It can either become more and more gentle, or it can move where 0.5 lies, it can move it around along the x direction. So that is how the sigmoid function moves around to fit the training data that you have been given. Okay. Okay. So let us talk about a sample application of logistic regression. How we use it, what do we do once we get the ideal W's and so on. Let's talk about that. I am going to use an example that we have looked at earlier, probability of default predictor when you're handing out loans to people. So you want to classify loan applications. You want to classify loan application as high risk by computing a probability of default, let us say. Okay. Or conversely, you could be finding the probability of the person successfully returning the loan, right? So that's what you're trying to do. Now your input vector x is the vector of values of certain parameters pertaining to the individual. Let's say his income, his credit score, his age, and so on and so forth. So this is the input vector which you construct. There could be more parameters. This is the input vector you construct by putting in the person's various parameters that you are gathering. Training data is the set of values for people who have defaulted and who did not default. Okay, so if you are finding the probability of default, then p equal to 1 would indicate a very bad loan. P equal to 0 would actually indicate a very good loan, 0 probability of default. And then you want to find out where in between these two extremes a given person lies, right? So the training data, it's again a supervised learning. Training data is a set of values for people who defaulted and who did not default. You know which values pertain to somebody who defaulted and you know which one pertain to somebody who did not default. We want to find the decision boundary W. We want to find the best weights W by using the gradient algorithm on log likelihood. This is what we want to accomplish. Okay, so here we have, everything that we have studied earlier. We have p equal to 1 over 1 plus e to the minus z is equal to this. And we showed how gradient descent algorithm can be implemented by implementing this particular equation. Your new weights are equal to your old weights minus this particular quantity. And you keep evaluating this quantity over and over again. You keep finding new weights till the time that your objective function no longer reduces, right? So you reach the global maximum or minimum depending upon whether you have put the minus sign or not. Now What happens when you finally reach the optimal W? How are you going to use your logistic regression model? When you find the best W, what you do is when you are given a person with certain input vector X, when you are given a test sample, so a test sample would be a person who you have not met before, whom you have not seen in the training data. He would also have some income, some credit score, and age, so on and so forth. So you are given an X, over here. You do W transpose X using the optimal W that you have found after doing gradient descent to find Z, and then you find the probability using the sigmoid function. And if P is greater than 0.5, he is tending towards default. If P is less than 0.5, he's tending towards not default, and the value of P itself is an indicator of how safe or how risky he is. If P is extremely high, he is very close to a default and you want to stay away from that guy. If P is extremely small, obviously you want to invite him and immediately give him a loan. And if P is somewhere near 0.5, 0.6, 0.4, etc., etc., it falls in a range where you may want to exercise some discretion and decide what to do. So there is a direct probability of default that you can find once you have found the optimal W's. So that is how a logistic regression mechanism can be used to build a probability of default predictor while issuing loans. Great. Okay, we are done with the three models and I want to spend a minute comparing all of them, right? So what are some of the things that one can say? I'm going to list a few points here. Some of these are, you can sort of justify them theoretically. Some points are empirical observations. However, I will just put together all the points under comparison so that you know when typically something works and something does not work. So for small data sets, naive Bayes and gradient and GDA, Gaussian Discriminant Analysis, are better than logistic regression. Okay, we already justified why NB is better, is a good model to choose when you have small data sets, because it's not a complex model. It is also observed that GDA does somewhat better than LR meaning logistic regression, when the data sets are smaller. Actually, I should say that typically GDA can work better on smaller data sets than LR, typically. Okay, but nothing to beat NB, nothing to beat naive Bayes. For small data sets with large number of features, so when the number of features is very high or not commensurate with the size of the data sets, small data sets with a larger number of features, NB works very well. The naive Bayes works very well in that situation, and we know why that is the case. It's a simpler model, its complexity is less, and therefore the variance errors are going to be less typically. And this is particularly true about problems like where you are parsing text, or where you have very sparse tokens, or for example where you are doing email versus spam and so on and so forth, right? For continuous correlated features, GDA is good. Okay, so if you have continuous features, if you are dealing with continuous variables, and if there is a correlation between your input variables, then the Gaussian discriminant analysis is good. Of course, correlated features rules out NB, it rules out naive Bayes, and then GDA does generally a better job than LR. GDA does a better job than logistic regression. For large data sets or tabular data sets, LR works very well. Logistic regression works very well when your data sets start becoming larger and larger. And if you are interested in high accuracy scores or accurate risk scores in terms of probabilities, LR typically works very well. The probabilities that it returns are usually more accurate, of course, if you have substantial data sets. So in this particular situation, you may want to go with logistic regression. Now, I want to emphasize that these are generally just what I have said are indicators. Many of them are based on empirical observations of other researchers, and normally what would be suggested is you do validation. We have seen what validation is. You divide the training data into a training data and a validation data, and running that sort of a validation is a good idea when you are experimenting with these three options, these three probabilistic models. So to compare LR versus GDA, to compare logistic regression with Gaussian discriminant analysis or naive Bayes, you are better off actually using validation sets and seeing what is working for your problem type. Okay, so I will end with a summary. I will end this lecture with a summary of what we have studied. We have seen that probabilistic models allow us to associate a probability with our classification result, which is very useful in many real world applications. We saw that there are real world applications where you want to know how much confidence the system has in the answer it has returned, and probabilistic models do that very well, right? Probabilistic models associate a probability. Probabilistic techniques can be generative or discriminative. We looked at this terminology in the earlier lecture, and in this lecture we have mapped it to the way probabilities work. We have linked it to the idea of probabilities, the model that you are building, whether you are doing a probability of y given x or you are doing a probability of x given y as your approach. That determines whether it's a generative model or a discriminative model. And we have also said that it depends upon the data at your disposal and what additional information you have about your parameters. Do you know the probability density functions and so on? If you know those, that will guide what kind of approach you take. And these are the three basic probabilistic models that we looked at: naive Bayes, Gaussian discriminant analysis, and logistic regression. So those are the models that we have covered. Okay, that brings us to the end of this lecture, and as always, I have a few questions for you. My first question is, what is the shape of decision boundary in logistic regression? If you have been paying any attention to the last half hour, this question should be trivial to answer. Okay, my next question is, what is the shape of the decision boundary in naive Bayes? Is it linear? Is it piecewise linear? Is it quadratic? I want you to look at how naive Bayes works and justify your answer. Okay, what is the shape of the decision boundary, the separator, in a naive Bayes model? Question 3. Okay, these questions are tricky. Manufacture a training set of 5 or 6 points where the class boundary for a linear classifier, okay, class boundary for a linear classifier, let us say by optimizing not MSE but the hinge loss is identical to the class boundary for logistic regression where you are optimizing cross entropy. Okay, so what I am saying is you choose the placement of training points. Don't do it in like many dimensions. You can just choose 1 or 2 dimensions. Take 5 or 6 points and come up with a placement of your training data so that the class boundary for a linear classifier by optimizing HL, hinge loss, is identical to the class boundary for logistic regression, which would be found by optimizing the cross entropy. All right, so that is the question. It's a tricky one. I don't want you to run some simulations and do this. I want you to think about how optimizing the hinge loss works. Think about how optimizing the cross entropy works. Cross entropy is of course a more complicated expression, but the choice of training set is in your hands. So you should be able to work out a training set where these are identical or at least as close to each other as possible. Question 4. Manufacture a training set of 5 to 6 points where the class boundary for a linear classifier found by optimizing the hinge loss is very different from the class boundary for logistic regression, optimizing the cross entropy. Okay, so this is the converse of the example in question 3. I want you to manufacture training data, select training data. You can select 1 dimension or 2 dimensions. I'm fine with that. Where the class boundary returned by the linear classifier is very different from the one returned by logistic regression. So the purpose of question 3 and question 4 is for you to think about how the placement of training data, how the training points move your class boundary in both of these cases. Linear classifier with HL as in hinge loss and logistic regression with cross entropy, right? That is what I want you to, that is the purpose of this exercise. My last question is, why does NB work better than LR on small data sets? Again, I have alluded to that in this lecture, but you have to explain this from a theory of learning perspective. We spent a long time on theory of learning, and I want you to justify why naive Bayes works better than logistic regression on small data sets. Okay, that's the last question. Okay, that brings us to the end of this lecture. Thank you. I'll see you again later.